So, why does a GPS satellite clock tick faster than the clock in your pocket, even though the satellite is moving at thousands of kilometers per hour? If engineers ignored that mismatch, your phone's location would drift by about 10 kilometers every day. Two identical atomic clocks can separate, reunite, and disagree about how much time passed without either clock being broken. A clock is any system that repeats reliably, like a swinging pendulum, or in an atomic clock, an electron and cesium flipping between two energy states. Relativity, confirmed by experiments, says those repetitions don't have a single universal rate. Speed can slow a clock, gravity can speed it up or slow it down, and GPS sits right at that collision. Gravity is a difference in clock rates from place to place, which is not what a simple pulling force suggests. Einstein's equivalence principle says a small sealed lab cannot tell the difference between standing on Earth and riding in a rocket accelerating in deep space. In that rocket, a laser pulse sent from the floor to the ceiling is received with a lower frequency, fewer wave crests per second, because the ceiling is moving away by the time the light arrives. That is the Doppler effect. The equivalence principle, therefore, predicts a similar frequency drop for light climbing upward through a gravitational field, called gravitational redshift. Because atomic clocks are built by counting electromagnetic cycles, gravitational redshift is a direct clue that lower clocks tick more slowly, pointing straight at the satellite and ground mismatch. If time runs slower at sea level, why don't you feel it? Every chemical reaction and nerve signal in your body slows in step, so your own second still feels like a second. The difference appears only when two clocks compare, either by exchanging radio signals or by leaving, reuniting, and placing them side by side. Physicists call the time a clock measures along its own journey proper time, and proper time can differ between two journeys, even when they start and end together. The Pound Rebka experiment in 1959 verified gravitational redshift by sending gamma rays, an energetic form of light, up a tower, and modern atomic clocks repeat the same comparison routinely, so the satellite versus ground disagreement is measured physics. A few dozen microseconds are enough to break a navigation system. GPS receivers compute position by comparing the arrival times of radio signals from several satellites, so a time error turns into a distance error at light speed. A microsecond of clock error is about 300 meters of location error, simply because radio waves travel that far in that time. The raw physics makes satellite clocks and ground clocks drift in rate by about a few dozen microseconds per day, so GPS satellites launch with their clock rates intentionally offset and then continuously corrected. Without that correction, the timing mismatch alone would build into about 10 kilometers of position error per day, which is why this is not an abstract relativity story. What happens when gravity is much stronger than Earth's? A neutron star packs more mass than the Sun into a sphere roughly the size of a city, so the clock rate difference between its surface and far away can be tens of percent. Astronomers test this by measuring spectral lines, very specific colors, from atoms near compact stars arriving redshifted, matching the same gravitational redshift logic as on Earth. Gravity even changes travel times. Radar pulses aimed at Venus and skimming near the Sun return slightly late in the Shapiro time delay, and gravitational lensing, the bending of light by a massive galaxy, can split one distant quasar, a brilliant galaxy core, into multiple images whose brightness changes arrive days apart. All these observations say the same thing GPS engineers rely on. Gravity changes how fast time accumulates. Time differences are not glitches in clocks. They reflect different paths through space-time, the combined arena of space and time. Each clock accumulates its own proper time, and proper time depends on both speed and gravitational height. For GPS satellites, weaker gravity up in orbit makes the atomic clocks tick faster by about 45 microseconds per day, while the satellite's high speed makes those clocks tick slower by about 7 microseconds per day. The gravity effect wins, so the satellite clock ends up about 38 microseconds per day ahead, exactly the mismatch engineers have to remove. The final twist reinterprets the opening. There is no single universal, now even on Earth, because a clock on a mountain, or at your head, ticks a tiny bit faster than one at sea level, or at your feet. Like if this was interesting, hit the subscribe for more, and turn that notification bell on.